Right, today we are covering vectors and coordinate systems. That is today. Just a quick outline. We're going to go a little bit of revision on the vector side. Going to have a look and see if you can multiply vectors, the dot and the cross product. And then we're going to do some relative and absolute motion and look at all the different kind of coordinate systems that you can get. Okay, so scalars is the quantity that's just got a magnitude, so there's no direction, nothing, it is just one value. That is usually mass, temperature, speed. You weigh a certain amount, kilograms. The temperature today is 20 degrees, I wish. And speed, I'm going at 60 miles per hour. Mass is a scalar, but weight is a vector. Vector quantities are designated in a boldface. There's different ways you can note them down. There's other ways you can go about doing it. You can underline it, you can give it a little hat, or you can put an arrow over it. So there's different ways of notating a vector, just be aware of it. Right, so there's essentially two methods where you can go and add vectors together, triangle method and parallelogram method. If you look at the A one, automatically you can see that that is a triangle with a 90-degree at one of its points. So automatically that can be, you can use Pythagoras rule to do any calculations with that vector, which is really helpful. And then the B is basically just another way you can notate it. So the vector R has got two components, A and B. You can almost say that also a vector in the notation, if you've got an x-axis and a y-axis, you've got an x-axis component and a y-axis component for that vector. So a negative vector is a vector with the same length, it's just in the opposite direction. A is a vector, boldface, and then the vector in the opposite direction has got a negative sign to it, and if you add them together, you get 0. So right, so if you consider vector A in a two-dimensional space, which connects the origin with point P, the projection of the vector on the x and the y-axis results in the number ax and ay, respectively. So that is the component going along the x-axis, parallel to the x-axis, as well as the component of the vector going parallel to the y-axis. So that is one way to do sort of notate that vector, and then you can use, if you know two of the three values, you can use Pythagoras rule to calculate the third value. All right, so then we go into three-dimensional vectors. There's a nice one. So now we start to use angles. In this one, we get the vector A that connects the origin with point P, and then you get the three components that go parallel to the y-axis, the x-axis, and the z-axis. But then you also get the angles phi and theta, which also then becomes important. All right, so whenever you want to notate vector in the three-dimensionals, you need the three components as well as the two angles. You can denote these axes, the AY, AZ, and AX. You can use the I, J, and K unit vectors. They call it versors, but it's basically a unit vector. Its value is 1. Its value will always be 1. So you can always just say I, J, and K, and they help you determine which component of the vector is parallel to the x-axis, parallel to the y-axis, and parallel to the z-axis. And then it's shown there, you can see in the red arrows which one is which. So the I is the x-axis component, the J is the y-axis component, and the K is the z-axis component. And this is the way you can write it. So essentially, the vector A equals any value, the magnitude, plus the I vector, unit vector, plus the I component, the y component, plus the J unit vector, plus the z component times the k unit vector. If you want to get the absolute or the magnitude of that vector, you use this notation where you square all three components and you add them together and you put it under a root, square root, and then you get the magnitude. So that's the magnitude of a vector by definition is always positive, because the fact that you square it, that will change any negative value to the positive. And these are the two angles that you can use. Theta and phi can be determined by trigonometry. Basically, that is the two equations that you're going to use to do that. And those two equations should get you through most of the problems if we ask you for any calculations in terms of vectors. If we know the angles and the magnitude of A, then the values AX, AY, and AZ can be determined. So that is just, again, based on trigonometry.
Right, let's do an example. Determine the magnitude and angles theta and phi of the following vector. And I've given the vector as vector A equals 3i minus 5j plus 6k. Now the first thing to do when we consider questions with vectors is to break the vector up in its corresponding parts. So we know AX is 3, AY is minus 5, and AZ is 6. Now the equation to determine the magnitude of the vector is to square all the different parts of the vector and sum them together and put them under a square root. And we get an answer for the magnitude of the vector A as 8.37. We can now go and calculate the values for the angles theta and phi, and we get an answer for theta as minus 59 degrees and for phi as 44 degrees.
Okay, next up is multiplication. So there are two types of multiplication you can get: dot product and cross product. So dot product, if you multiply two vectors by using the dot product method, you'll get a scalar. So that is just the magnitude, no direction. If you use the cross product, you'll just get another vector, different magnitude or different components, different direction. So the dot product is, you can write it down as the A vector with a little dot and the B vector. That's quite self-explanatory from the name dot product. Two methods on how you can calculate that: analytical and geometric. So that is essentially how you note down a dot product. You multiply vector A's z component with vector B's z component, and similarly with the other components, and you add them all together and you get the magnitude, which is a scalar. No longer has a direction, like I said. The coefficients are multiplied together, so they cancel out, and the results are all summed up, and you end up with one value. Geometrical method is, as you can see now, you go and you visually sketch it, vector A and vector B with an angle between the two of them, and then you can calculate the magnitude of vector B multiplied by cos alpha will then give you the answer as well. So that's another way. That's a geometrical method. Yeah. All right, so there's an example which we can have a go at. So there's two vectors, A and B. The vector A has got three components, I, J, K component, and vector B has only got two. So find the magnitude or the dot product of those two vectors. All right, so there's the answer. You get 14. Because the B doesn't have an I component, it's essentially 0. So 0 times 3 gives you 0, so you can just disregard that. Negative 5 times 2 is negative 10, plus 6 times 4 is 24. 24 plus negative 10 gives you 14. And you can see that it's just the magnitude. There is no direction on that. All right, there's example 2. A vector has just got the I component, the I unit vector, so that's essentially 1 times I. And the B component has just got the K value. Now, based on your experience in example A, what will be the answer here? 0, yes, exactly, 0. All right, we're moving on to the cross product. So now it gets a bit more interesting. It's not anymore that nice and straightforward as the dot product. Now you are generating a completely new vector. So if you use the cross product from vector A and B, you get a new vector C, and that has a direction. So that is, which makes it a bit more complicated. So again, there's two methods of doing that. Get the analytical method involves setting up a matrix and calculating its determinant. So there is the matrix. And then they use these guys' rule, Sarris's rule. We can see that the determinant is this equation. Yeah, like I said, so those are the x, y, and z components. Like I've shown you those three circled. We can also write C similarly to A and B is in that notation. Geometrical method is the second method. Again, A and B, you can write it down or sketch it with an angle between the two. And the magnitude of the cross product, again, is given by that equation there. So the magnitude of A multiplied by the magnitude of B, sin alpha. That is the geometrical method of calculating the magnitude of C. Cross product is 0 if the angle is 0 or 180. Essentially, if you think about sin 0 and sin 180 is 0, by looking at this equation at the bottom, sin alpha, if the angle between the two vectors are 0 or 180, then automatically the cross product will be 0 as well. Okay, and equation C provides the magnitude, but what is the direction? So we use the right-hand corkscrew rule. So it is the little circle with the cross between it. The way you can remember that's an arrow. If you look at the arrow from behind, it's the feathers which makes the cross, so it's going into the page, you're shooting it into the page. If it's going a circle with a little dot, it means the arrow is coming out of the page towards you, so that's outside. So we can basically say that that is true. Vector A times vector B equals the negative vector B times vector A, so they are opposites of each other. But that is not true. So just make sure you remember that. Vector A times vector B equals negative vector B times vector A, but it's not, you need that negative sign, because essentially it's the same vector, the direction is just different.
All right, let's do an example. Determine the cross product A cross product B with the A vector and the B vector given as shown. Now from the equation that I just showed previously, we can get a new vector C by using this equation. If we substitute all the bits from our vectors A and B into this new equation for C, we get the answer for C as 28i minus 24j plus 10k.
All right, next up is relative and absolute quantities. Again, if we use vectors, we can consider 2 points, or consider positions of 2 points A and B relative to a third point O, O being the origin. Yeah, O being the origin of the coordinate system. Then there's a few ways you can write these vectors. So this, you use the subscripts. RAO is the vector giving the displacement of A relative to O. So that's always the first subscript A is the vector or the position or the point that you're considering. And then the second subscript later is from where you're considering it. So in this case, RAO, you're considering point A, and you're standing at the origin, essentially. The same for point B. If you're looking at point B from the origin, RBO is the vector giving the displacement of B relative to O. And then you get a third one, which is RBA. Again, you are considering point B, but now you're standing at point A. So that's relative versus the other two being absolute. And you can just write them as RA or RB. You don't need to write the O because they're absolute values. You don't really need to write the O there, but you can if you want to. Keeps it a bit simpler and doesn't make you, you know exactly what you're talking about when you say RA or RAO and RBO. And then the relative displacement is then anything that's not from the origin. You're not looking at it from the origin, or you're not observing it from the origin like RBA. So now you're looking at the displacement of B relative through A. This notation is quite important because it can change. We can look at RBA, but we can also look at RAB. So that's point A while standing at point B. So you do need to make sure you understand the subscripts, because that can make a big difference in a problem that you're solving, and you got it wrong, then your answer will be wrong. So just make sure you understand those subscripts. Again, you can just add it together. So RBO, which is the absolute displacement, is the absolute displacement RAO plus the relative displacement RBA. That's how you can add them together. And you can just rearrange it, play around with it, and you can decompose it as following as well. So it's essentially, it's just a vector which can be broken down in its components, and you can also again use dot product and cross product using those vectors. Just be aware of the differences being relative or absolute displacement is quite important. All right, then we can also get the velocity. We can get absolute velocity, absolute or relative velocity by just differentiating the vectors. So the displacement vectors are, you can get r dot, which is essentially v, s for being displacement, v being, or u and v being speed, and a being the acceleration. In this case, r is the displacement, r dot, r double dot is acceleration, or you can just say v, it's the same. All right, so there's just a quick example to sort of demonstrate relative and absolute movement. So car A is traveling due east at 30 meters per second. Due east, meaning it's the positive x-axis if you want to put it onto a coordinate system, and it passes the second car B traveling at 20 meters per second. It's traveling slower than car A. To calculate the velocity of A relative to B if the cars are moving in the same direction. All right, so car A's velocity will be r dot equals 30i, and car B's velocity will be r dot equals 20i. And now if they're moving in the same direction, basically just go and subtract them from each other. So then car A appears to the observer in car B to be moving more slowly than it really is. And everybody, I think, has experienced that when you're overtaking someone on the road. You're going at 70 miles per hour, the guy's going at 60 miles per hour, and then when you pass them, it looks like they're going at 10 miles per hour. That's essentially what it means, relative to you. Obviously, relative to someone standing on the side of the road, which can be taken as the origin, that will be 60 miles per hour and 70 miles per hour. So that is the difference when you are considering someone from the origin versus relative observation where you are moving as well, or something's happening to you while observing. All right, if it's B, I think is opposite directions. Yeah, opposite directions. So then in this case, 30i is still traveling due east, but now the other car is traveling due west, and because it's going negative x-axis, you get the negative 20i, and if you subtract them from each other, you get 50 meters per second. So now it looks like car Yeah, so car A appears to the observing car B to be moving faster than it really is because of the opposite direction. This is another example. So this is a river. So the river has got a width of B equals 100 meters, and it flows west to east. So west to east, you can see there's a little west to east, so from left to right, and it's flowing at 3 meters per second. So V subscript water is 3 meters per second, which is also 3I meters per second. Right, the small motorized boat, which can travel through still water at 5 meters per second, is used to travel from point on the south bank to the point directly opposite to the north bank. So that is from the origin O to the other point directly opposite, which is point P. Now we need to consider what is the vector VB, which is the velocity of B relative to O, the origin. And to do that, we need to work out VB. Now this is using the trigonometry sort of way. So if you look at that triangle there, you got the 3 meters per second, which is the adjacent side of the triangle, and you've got V subscript BW, which is the diagonal part. You can use that as arc, just get it, yeah, sin, the inverse of sin, and you can get the angle. And once you've got the angle, you can then calculate the last unknown side of the triangle. But you can also use Pythagoras' rule, because that triangle's got a 90-degree side, 90-degree point. So that's basically just 5 squared minus 3 squared underneath the square root, and that'll get 4 meters per second. So that's another way you can do it. But then you don't need the angle, so you haven't calculated the angle. So if they want you to calculate the angle, then you just calculate the angle. And then there's a nice little question, the time to cross the river. So we know the distance is 100 meters. We know it takes 4 meters per second. That's 25 seconds then to cross the river.
Right, let's do an example. The question states that a man walks 4 kilometers north and then 5 kilometers east. And you need to go and calculate the resultant displacement of the man. That is, how far and in what direction he is from his starting point. Now for this question, we are going to denote upwards as positive y, that's north, and east as positive x. We can thus say ax is 4 and ay is 5. Now as this is a right angled triangle, we can get the value for the unknown component of this vector az, and we get the answer of 6.4 kilometers, which is the resultant displacement of the man from his starting point when he started walking. The angle theta at which this vector is orientated can be calculated with the equation shown, and we get an angle of 38.7 degrees.
All right, so we're moving on. Again, just covering the right-hand rule. There's a nice little picture showing you how to do the right-hand rule if you do a cross product. So to use the right-hand rule, hold up your thumb, index and middle finger. Index finger presents A, which is the first vector in this case, and the middle finger, which is perpendicular to the index finger, represents B, the second vector. So if you've got cross product A, cross product B, A will be the index finger and B will be the middle finger. And the direction of the cross product is the direction of the thumb. So if that is positive or negative, again, into the page, out of the page. It's good to go and draw a little coordinate system to sort of help you with that. So you can see there, number B is the IJK. Those are the positive directions for the coordinate system. Applying the right-hand rule, we can see that the direction of the resultant vector is in the positive direction. A times B is I times J equals K. If you use that B, which is your coordinate system, it's not going to be really nicely visible, but essentially you're going to have to go and say K, which is your index finger. So K goes up, J goes to that side. So then your I goes literally diagonally from left bottom to right top, which is the opposite direction of the x-axis, which makes it negative, and thus you get negative I. Displacement, velocity, and acceleration. The same goes for this one, where you get a displacement RT, and then similarly you can just go and get the velocity and the acceleration of both. By just differentiating it twice, you get the acceleration. And that will be differentiating each component of that vector. Little last paragraph, the problems we face in dynamics can often be decomposed into x and y components, each of which can be analyzed separately. Only together describe the motion of the particle fully. All right, lastly is alternative coordinate systems. So the one that we've been covering with the x, y, and z is not the only ones. There are two others. namely, or three others, namely polar, cylindrical, and spherical. That comes to mind if you've got something that's rotating, like for instance a hammer thrower who's going round and round. You can more easily give the movement of the ball of the hammer. You can notate it more easily in polar components or even spherical or cylindrical rather than the x, y, and z components. It's up to you really. So here's just an example of the polar coordinates where you usually have the vector A, which can be broken down into its two components, the x and the y component. You can also write it down as just the magnitude and the direction theta from the x-axis. So that's another way, that's the polar coordinate system. Then we get the cylindrical one, which is, again, you get your vector A, and then you get the z component and some a dash one, which is characterized by, again, by another direction, another angle. So you write it as the magnitude and the two angles. Oh no, that's the spherical one. This is still the cylindrical. Oh, there we go. Vector defined as a dash, then theta, and then the z component of a. So that's the spherical, cylindrical polar coordinate system. All of these can be converted just by using regular trigonometry equations. You can convert from one coordinate system to another. You can see still by just looking at that picture, you still got your x, y, and z axes. So I mean, by just doing that, you can easily take this back to the x, y, and z components just by using trigonometry. Then lastly, spherical polar coordinates, and then again it's notated like there at the bottom, where you get the magnitude of the vector A, and you get the two angles, theta and phi. Yeah, trigonometric relationships can be used to switch between those coordinate systems.
So in summary, we did some revision on vector addition and vector decomposition. We also looked at vector multiplication, the dot product and the cross product. I also discussed relative and absolute quantities, and we looked at displacement and velocity vectors specifically. And lastly, we also looked at the different coordinate systems, the right-hand coordinate system and alternative coordinate systems that are out there. And that's it. I am available on LinkedIn and Twitter. If you've got any questions, please do not hesitate to ask them, and I will be more than happy to answer them. Thank you very much for watching, and I will see you in the next video. Bye.